So welcome to this. This is the Further Math Support Program online revision for OCR Statistics 2. And in this session we're going to be looking at the Poisson distribution. Now the Poisson is a really cool distribution and what you need to be aware of is when you can use it. So for instance, you know that the binomial, you need to have things like events have to happen independently, you have to have a fixed number of trials, p cannot change over your duration. Well, with Poisson we've also got conditions. So first of all, events occur at a constant rate. Okay, so we're dealing with rates here, so we're looking at things like how many cars pass in 1 hour. Okay, and it's all about that. They have to happen singly in time. So in other words, you can't have, in that example, 2 cars passing at the same time. And also they have to be independent. So the fact that a car has passed, say of a particular colour, doesn't necessarily mean that a car has also passed. Now, the parameter sometimes is mu, is also lambda. Okay, so you'll see in questions both of these, and the reason is it's because it's also the mean. The rate is also the mean in lots of contexts, so you just need to be very aware of that. The reason we use PO for this distribution is because P stands for probability. Okay, so we need to be able to calculate these probabilities, and a lot of that, like the binomial, is used from a table. We also need to be able to work out or know that expectation and variance are the same, which are also equal to mu. And this is the cool bit, we can sometimes use the Poisson as an approximation for the binomial, as long as it's appropriate to do so. So for instance, we have to have large n and we have to have small p. So it's done in such a way that n is sufficiently large and p is sufficiently small that actually NP is less than 5, and that's the sort of standard sort of condition that we're looking for. Okay, so June 2010 question 1. Number of inhabitants of a village who are selected for jury service in the course of 10 years is a random variable with distribution Poisson 4.2. Okay, now the time frame is incredibly important with these, as you'll see in a minute. So it says find the probability that in the course of a 10-year period at least 7 inhabitants are selected. Okay, so we're looking at the probability that x is greater than or equal to 7. Now we have cumulative tables for these, so we need to be able to turn this around in the same way that we would with the binomial so that we get cumulative probabilities. So we're looking for really the probability of x being less than or equal to 6. So we look at 4.2 as your value of lambda, and we're looking up 6 as my probability. Okay, so we have tables and this is great. So the probability of x being less than or equal to 6 is equal to 0.8675. Okay, so the probability of having at least 7 will be the complement of that. So it's 1 minus that, so 0.1325. Okay, so that's great. You get 2 marks for that, which is lovely. 1 for switching around your probabilities and therefore using the table, and 1 for getting the correct answer. Okay, so we're then asked to find the probability that in 1 year exactly 2 inhabitants are chosen. So you need to realize this is a 10-year period of Poisson 4.2. So let y be the number in 1 year. So what it turns out is that y can be modelled as a Poisson of 0.42. Okay, if we expect 4.2 in 10 years, we would expect 0.42 in 1 year. Now, you don't have a Poisson table for 0.42, so we have to realize that we're going to need to use a formula, and there is one. It's the probability that x equals a specific value is equal to e to the minus lambda times by lambda to the power of r over r factorial. And you're given this in a formula booklet, so that's great. So in this particular context, we're looking for exactly 4, should be y in my case, exactly 2, sorry, so that's going to be e to the minus 0.42 times by 0.42 squared over 2 factorial. And if you whack that into your calculator, you're going to get 0.05795. Okay, and any answer that rounds to 0.58 will be fine. You can, in theory, interpolate from the tables, but it's not advisable and it takes too long. Okay, so 3 marks for this. Okay, you get a method mark for recognizing we're dealing with Poisson 0.42. We then get a method mark for using the formula correctly and an accuracy mark for getting the correct answer. We're then asked to explain why the number of inhabitants who contract influenza in a year can probably not be well modelled. So this is asking for you to look at the conditions of your Poisson. Okay, and there are a variety of things, but it's got to be in context. That's the critical thing. So in this case, what I'd be saying, one thing I could be saying is catching influenza is not independent. Okay, the fact that somebody's caught it probably means that somebody else is going to be, and this is because it's contagious. Okay, so contagious diseases don't necessarily follow this Poisson distribution. Okay, or you could argue that the rate over the year is not constant. Okay, pure and simply because more people are going to contract flu in the winter than they are in the summer. So there are two sort of answers you could ask there. And you get 2 marks here. You get 1 for stating, in this case, that you're looking at lack of independency. Okay, sorry, these are B marks. And then you get your second B mark for making sure it's in this context. Okay, so if you just write not independent, you're not going to get a mark. Okay, so it's got to be in context. That's the key thing with that. Okay, so January 2011. Question 3. The probability that a random choice P phone has a fault is this. A random sample of 200 is obtained. So you need to realize before we even think about reading the rest of the question, this is really a binomial distribution. Either they have a fault or they don't. So that's really quite important. And we're asked to use a suitable approximation. Okay. Now, it's very important to check n times p. So if you do n times p in this particular case, you're going to get 4.56. So we can see that this is less than 5. So it makes sense that we are able to do a Poisson approximation. If it was greater than 5, we'd be looking at the normal approximation. Okay, so it's quite important that you're aware of those being correct. So what this means is that x can be approximated as a Poisson 4.56. So that's fine. So use a suitable approximation, so we've dealt with that, to find the probability that the number of p phones is 2 or fewer. So we're asked to calculate the probability of x being 2 or fewer. Okay, and we've got to justify your approximation, so we've done that here by discussing np being less than or equal to 5. Okay, so n large, p small, np less than 5. So that's what we want. Okay, so n large, np less than 5 would be sufficient there. Okay, so again you recognize that 4.56 is not in your Poisson table, so to calculate this we need to realize that it's the probability of x equaling 0, 1 or 2. So we've got a little bit more work to do here. Remind you of the formula. So the probability of getting a specific value is equal to e to the minus lambda, lambda to the r over r factorial. So what we can notice in this is e to the minus lambda is a common factor. So I can actually take that out just to make my life a little bit easier. And that's going to leave me with 4.56 to the 0 over 0 factorial plus 4.56 to the 1 over 1 factorial plus 4.56 squared over 2 factorial. Okay, and that can then just be calculated, which is quite nice, which is going to give me 0.167. Okay, so this is a really nice question. It's just got to make sure what you're able to do. So let me just change pen and I'll show you where your marks are awarded. So in this particular case, you get 1 for recognizing that it's binomial, which is quite nice. You get another mark, this time it's an accuracy mark, for using the correct approximation. You then get 1 mark for starting to use the Poisson distribution and using the correct formula, and then you get 2 accuracy marks for doing these things. Your final mark, which is a B mark, is for your justification. Okay, so that's actually quite a nice question. Okay, so June 2011, question 8. We've got a group of students discussing the conditions that are needed if Poisson is to be a good model for the number of telephone calls received by a fire brigade on a working day. Alice says that events must be independent. Explain why in this condition, why this condition may not hold in this context. So basically, if you think about it, if there is an incident that occurs, you're going to get lots of people phoning. Okay, so several calls may refer. Okay, so several calls may refer to this incident. So it's not really independent. The fact that somebody is calling about an incident is not independent from the fact that somebody else is calling about an incident. Okay, so again, you need it in context to be able to get this mark here. Okay, otherwise it's not going to get there. Okay, so state a different condition that is also needed and explain whether it is likely to hold. Okay, so we need calls to occur at a constant rate. So that's a condition. And again, if you don't mention the word calls, you're not going to get your first mark. So we now need to know why. Okay, it's likely to hold or not. Okay? Well, the answer is no, not really, because over the course of a day, the call's not going to be consistent. Okay? Incidents that are going to be reported are probably less likely in the evening, so less likely at night. Okay, so we don't have really a constant rate. So you get 1 mark for stating another condition, and you get another mark for saying whether you think it's true or not. Okay, you could also, it's got to be within a day because we're talking about a day. So if you start talking about things like, in summer you're going to get more incidents than in winter, that's not going to work because we're talking about a specific 24-hour period. Okay, so it's just making sure in context that things are correct. Okay, so in the next part of this question, we've got 3 random variables, r, s, and t, and they're all independent Poisson distributions with lambda, mu, and lambda plus mu. Okay, and we're dealing with the case where lambda is equal to 2.74. We've got to work out the probability of being greater than 2. So first of all, you need to realize that that's the same as 1 minus the probability of r being less than and equal to 2. We also need to be aware that 2.74 is not in your tables. So again, we've got a situation where we're going to be doing 1 minus the probability that r is equal to 0, plus the probability that r is equal to 1, plus the probability that r is equal to 2. So again, formula time, 1 minus e to the minus lambda. That's a common factor, so we can pull it out. 2.74 to the 0 over 0 factorial, plus 2.74 to the 1 over 1 factorial, plus 2.74 squared over 2 factorial. Okay, and you can work that out really quite nicely, and that's going to give you 0.5161. Okay, so 3 marks. You get 2 marks for using the formula correctly here, and then an accuracy mark at the end. We've then got, in the case of lambda equals 2, mu equals 3, we've got to find the probability that getting 0 in r and s equals 1, or 1 and s equals 0. And we've got to give the answer to correct to 4 decimal places. Now they are independent. Okay, so that's really, really important. So really, this is the probability of r equaling 0 and the probability of s equaling 1. Or the probability of r equaling 1 and the probability of s equals 0. So we know that, we can do that because they are independent. Okay, so in each case, this is now going to be, it's going to be e to the minus lambda times by lambda to the power of 0 over 0 factorial times by e to the minus 3 times by 3 to the 1 on 1 factorial plus e to the minus 2 times 2 to the 1 over 1 factorial times by e to the minus 3 times by 3 to the 0 over 0 factorial. Okay, so simply by writing that, you've got 2 marks. You've got your method and your accuracy mark. Okay, which is really nice. And then we calculate that to give us 0.0337, which is where your final accuracy mark kicks in. So they're really testing whether you understand and remember what independent events mean in terms of probabilities. Okay, so a little bit of S1 thrown in there for good fun. Okay, so in the general case, what we've got to show is this statement is true. We've got to show that the probability of r equals 0 and s equals 1 and the probability of r equals 1 and s equals 0 is exactly the same as the probability of t equals 1. Okay, and we've got to do it in the general case. So this time, we don't have our things. So r is a Poisson lambda, sorry. S is a Poisson mu, and T is a Poisson lambda plus mu. So we're going to start with the left-hand side, so it's a good idea to do this separately. So again, we can replace and with multiplications, okay, which is quite nice. So it's the probability of getting a 0, which is that, because it's lambda naught over naught factorial, don't need to worry about that. And the probability of getting a 1 is going to be e to the minus mu times by mu. Okay, or e to the minus lambda lambda times by e to the minus mu. Okay, so that's what we've got there. And we can notice something. We can notice that e to the minus lambda plus mu is a common factor. We get mu plus lambda. Okay, so that is the left-hand side. So that's quite nice. Then you can do the right-hand side. So the right-hand side is the probability of t equaling 1. So that's going to be e to the minus lambda plus mu times by lambda plus mu to the power of 1 over 1 factorial, which we can see is e to the minus lambda plus mu times by lambda plus mu, which is equal to the left-hand side. So I've shown that the left-hand side equals the right-hand side, and that's absolutely fine. So that's quite a nice question. So let's show you how your marks were awarded. We can ditch 1 factorial throughout and 0 factorial because we know that it's 0 and 1. So you get 1 mark for getting this statement correct. You get another method mark for recognizing that e to the minus lambda plus mu is in fact a common factor. And then you get an accuracy mark for getting the correct left-hand side. You then get your final mark for either then stating that this is the same as the right-hand side, which I don't particularly like, or by actually showing that the right-hand side, the probability of t equaling 1 is exactly what it is. So that's a really nice question, testing your understanding about independent Poisson distributions. Okay, and it's always true, by the way, this statement, because you've proved it. Okay, so that's pretty much everything about the Poisson. Again, you need to be able to use the cumulative frequency tables, you need to be able to use the formula, you need to do approximations, and you are expected to think about it a little bit as well. Okay, so work through the exam questions, and everything will be great.